Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series which are presented for the BSc Physical Sciences students for the paper on applied electronics. We have been going through the chapter on quantum mechanics. We have seen in the last lecture the postulates of quantum mechanics, or the basic principles upon which quantum mechanics has been built. Naturally, we have to have an equation which will deal with the quantum mechanical systems, which will be obviously the Schrodinger wave equation. And so, the contents are as follows: Schrodinger equation, Schrodinger time dependent wave equation, wave function, physical meaning, probability densities, and expectation value. It was Erwin Schrodinger who lived from 1887 to 1961 who revolutionized and made us to have a proper and better understanding of electrons in atoms, molecules, and solids. We have an equation named after him. It is the most fundamental equation in quantum mechanics, the so-called Schrodinger wave equation. As I told you in the last lecture, it is a quantum analog of the equation given by Newton in classical mechanics, which is nothing but F is equal to ma. That, of course, all of you would have studied. The force is equal to mass into acceleration. It is a very important equation. All the mechanical engineers should follow the equation. Not only mechanical engineering, all engineering and other branches of science where you have the classical systems or the macroscopic systems, they should all obey the Newtonian equation. But on the contrary, when you go to microscopic systems like electrons and protons, that equation which is given by Newton should be replaced by an equivalent equation which bears the name of Erwin Schrodinger. The scientist only imposes 2 things, that is what Schrodinger said, namely truth and sincerity, imposes them upon himself and upon other scientists. How to deal with the electron? You start with the Bohr atom model and you go to the vector atom model, Pauli principle, and so on. You keep on increasing in the basic understanding of electrons. It is an evolutionary process. So, in the evolutionary process, Schrodinger equation comes in the way. And how do you arrive at the Schrodinger equation? You take a classical wave equation. What I mean by classical wave equation is, it would have been better, you can think of a string which I am having in hand, You imagine that I have got a string, I have a string is a classical thing, or you drop a stone in a pool of water. What do you observe? You generate a wave. It is a classical wave where water particles are moving up and down. You drop a stone in a pool of water, you are able to generate wave, or you go to the beach, you see nice waves coming towards the shore. So, these are the classical waves. So, in the classical waves, you have the classical wave equation. What is meant by classical wave equation? It is equation which tells you about the displacement cost on the water particle, or the displacement cost on the violin string. In the violin string, as C. V. Raman did, how the waves are developed or produced in the string, or you take a normal string, a wire, you vibrate it, right. You see the nodes and antinodes, and the displacement cost and the maximum displacement cost will be called the amplitude. You express the displacement in terms of maximum displacement called the amplitude. And who gave the classical wave equation? I will come to that in a minute. The de Broglie wave description was not suitable to explain the electron properties under different types of external potential fields. What is the de Broglie wave? Lambda is equal to h by p, that is the wavelength of the wave is equal to h by p, the momentum. You know, as far as light radiation is concerned, it has dual nature, and also for the particles like electrons, they also have duality, the dual nature. You should not consider the electron always as a particle. Hereafter, when you are in a quantum regime, you are using the Schrodinger wave equation, which takes care of or takes into account the de Broglie expression, the de Broglie wave equation, which connects the particle aspect of the particle and the wave aspect of the particle. So, the particle and wave aspects are fused through the Planck's constant. So, Erwin Schrodinger realized this, and so he derived an equation that conserves energy using his wave function to describe the electron. So, the description of the electron hereafter will be given by an equation of this kind, the so called Schrodinger wave equation. This is a very important equation. This will be used in any book on quantum mechanics. There are a number of hundreds of books on quantum mechanics. When you want to study all the problems dealing with electrons, protons, neutrons, and so on, and all the properties, right, electrical conductivity or semiconductors or superconductors, you talk of electrons and so many other ons. All these ons will be dealt with using this fundamental equation. The equation goes as dou square psi by dou x square plus 8 pi square m by h square into E minus v into psi is equal to 0. What is psi? Psi is called the wave function. You take the second derivative with respect to x, x is the position coordinate, then you have got 8 pi square m, m is the mass of the particle, it may be electron or a proton. Two body system is the well known Planck's constant, E is the energy of the particle, and V is the potential energy of the particle, and psi is again the wave function. So, when you take the Schrodinger wave equation, I will ask the question, what is the input? What do you want to get from the Schrodinger wave equation? Whenever one writes the Schrodinger wave equation, you should give some input to the problem. The input is the potential energy. The potential energy is the input, right? The outputs are E and psi. The energy of the system, the energy of the electron in hydrogen atom, or energy of the electron in some other atom, or the energy of proton, in the nucleus. Now, E is the energy system, that is the output, and psi is also the output. So, try to remember that the input is the potential energy. Okay? The other things are constants, right? You want to get out the two things, the outputs are psi and E. Okay? Now, what are other things? You have got the unknown things are psi and E. V is the input energy, the potential energy. M cannot be changed, a mass of the particle. H is the Planck's constant. Only three things are there: E, V, and psi. Okay? And E and psi are the outputs. By solving the Schrodinger equation, very often the teacher will be telling, solve the Schrodinger equation for the hydrogen atom problem. I will also be doing in the lectures to come, solve the Schrodinger equation for a particle in a box problem. Solve the Schrodinger equation for the hydrogen atom problem. Solve the Schrodinger equation for the harmonic oscillator problem, or the LHO, linear harmonic oscillator. Solve the Schrodinger equation for a rigid rotator. A rigid rotator is nothing but you have two atoms like HCl, hydrogen chloride, hydrogen atom and chlorine. It is a two body system. Hydrogen chloride, it is a molecule. It will be rotating. The rotation energy levels ought to be calculated. E is the rotation energy levels for the molecule, right. Similarly, the atoms in solids are vibrating, they are a harmonic oscillator, they are oscillating, they are vibrating. The vibration energy states ought to be known. So, the vibration energy states will be E. So, E will be either the rotation energy or the vibration energy, or simply the energy of the electrons which are being continuously being excited by the passage of electric current in the mercury vapor lamp, and the excited electrons, they come back to the ground state during which they emit light. So, they are incident on my face. So, how is it that you are able to see me? Because of the light that you have got here. What is light? Light is nothing but photons. How do you get photons? Because the electrons are coming from higher energy levels to lower energy levels. That is how you get photons. So, the energy of the electrons in the mercury vapor atom that you got mercury vapor lamp. So, the energy of the electron or atoms or molecules, they can be obtained by E is the energy, and psi is the state of the electron, the wave function, and V is the input that you should give. For all the problems, you should know the input. The input should be given, then you ask for the output. Then you solve the equation for different potentials applied to the electron. His description has proven to be correct after much use and is now considered the basis of modern understanding of the electron. So, whatever understanding we have got with regard to electrons in atoms, molecules or solids is due to the Schrodinger wave equation, which here the heart of quantum mechanics, the most important or most fundamental equation in quantum mechanics. It is one of the postulates of quantum mechanics that a physical system consisting of a particle, there is an associated wave function that determines everything that can be known about the system. The wave function is very important. The wave function is assumed here to be single valued function of position and time, psi as a function of x and t or r and t, since that is sufficient to guarantee an unambiguous value of probability of finding the particle at a particular position and time. This I will deal in a greater detail in the time to come. The wave function represents the probability amplitude. This is called the wave function psi. It gives what is called the probability amplitude. First of all, I should tell you, in the Schrodinger wave equation you got psi here, and psi is called the probability amplitude. In the classical wave equation, which I will be showing in a moment, you have a wave on the surface of water. By dropping a stone, you develop or form a wave, right. you can see the wave, right, by human eye. The wave is the crust and trough. The water particle goes up, at some other point the water particle comes down, or in the violin string or in the wire or in a string you can see the displacement, right. At this point of time I will have a break and we will have the rest of the break. Welcome back to the break. I have been telling you just now about the displacement caused or the disturbance caused on the surface of water. You have a pool of water in a tank, or you go to the seashore, see the wave. So, how the wave is developed, or when the disturbance is taking place in a medium, or in a string you get loops, you get you have the displacement caused. The wave is the one that can be observed by the human eye, but the most important thing is this psi cannot be observed. The displacement caused in a classical wave, that is a wave developed on the surface of water or the wave produced along the length of the string, those things can be observed, but psi cannot be observed. What can be observed is psi star psi. That is very important. The probability of finding the electron at a particular point, psi star psi, can be measured and experimentally verified and comparison made between experimental value. You go to the next department wherein you can make use of X-rays and you can determine the electron density. The electron density can be experimentally measured, and theoretically the probability that you got psi star psi, the theoretical electron density and the experimental electron densities can be compared with each other. So, psi star psi is the one that can be determined, but psi cannot be observed. Psi can be evaluated by psi, cannot be observed by psi star psi, can be measured and using a neutron diffractometer or X-ray diffractometer. You have XRD, X-ray diffraction or neutron diffraction. So, the electron density can be measured. Psi cannot be measured. Psi cannot be measured. That is important. The probability amplitude cannot be measured. Psi star psi is the one that can be measured. And again, the wave functions I am talking about should be normalized. What is the condition for normalization? The condition for normalization is the integral that you have got here over psi star psi d tau or dr. Dr is the volume element, should be equal to 1. Since the probability must be equal to 1, what is the probability? You take the hydrogen atom again, you got only one electron, so it should be equal to 1. Okay. In other cases also it will be made equal to 1. Then you come across what is called the normalization factor. Supposing you got 3 electrons, then what should I do? Psi star psi dr, there are 3 electrons, will be equal to 3, right? So, how will you make the right hand side to be equal to 3? You take this 3 to the left hand side, you have got 1 by 3 here, and you can have 1 by root 3 psi star multiplied by 1 by root 3 psi dr will be equal to 1. Okay? You take the 3 here, and this 1 by root 3 times psi is called the normalized wave function, right? I hope you understand the point, right? You have got n here on the right hand side, then you take n to the left hand side, 1 by root n times psi is the normalized wave function. Anyway, the point is the thing that you have got on the left hand side should be made to become equal to 1. So, sum of all the probabilities for all of space must be equal to 1. So, the right hand side should be equal to 1, the left hand side may be 1 by root n multiplied by psi, that is called the normalized wave function for a n electron wave function, n electron system, and that should be equal to 1. Okay. This is called the normalization condition, right. Let us now move on to the time independent Schrodinger equation. I am going to the heart of the problem and how the equation that I showed is arrived at. For that, as I told you, you go to a classical problem, the classical wave equation, the wave equation that governs a mechanical wave, a wave that is produced on the surface of water. You drop a stone on a pool of water, you get a wave, right? And that wave equation was is so called classical wave equation, right? In the classical wave equation, which was written by D'Alembert, and many people have worked on the classical wave equation. That is, any wave that you talk about should obey the equation, the most fundamental equation. The one dimensional equation was given by D'Alembert in the year 1711. The French mathematician and physicist D'Alembert gave the equation which goes as dou square u by dou x square equal to 1 by v square into dou square u by dou t square, and hence obviously u is a function of x and t. At a point along the length of the string, you have the vibration, right? You have the pool of water at any given point x. What is the displacement cost? The displacement cost is u, right? The displacement cost is u, and I may have the maximum displacement cost as u naught or something else, that is called the amplitude. Okay. Anyway, this is the so called the classical wave equation. Again, the most important thing is what I am going to do is I am going to make use of the de Broglie matter wave concept. I will reproduce. I will tell it once again. I am going to introduce the de Broglie's matter wave concept. What is matter wave concept? I told you about the dual nature. Electron should be considered both as a particle and a wave. So, the expression that is arrived at by Louis de Broglie connecting lambda and p will be made use of here. That gives you automatically the Schrodinger's time independent equation. Okay. By introducing the separation variables, you can write u x t. U is a function of x and t, obviously. It is psi of x multiplied by f of t, and psi is called the wave function or the probability amplitude. We obtain here f of t into d square psi by dx square, that will be equal to 1 by v square into psi of x into d square by dt square multiplied by f of t. If we introduce one of the standard wave equation solutions for such as e power I omega t, we obtain d square psi by dx square to be equal minus omega square by v square into psi of x. Okay. Now, we have an ordinary partial differential equation describing the spatial amplitude of the matter wave as a function of position. The energy of the particle is the sum of the kinetic energy part and the potential energy part. This is the kinetic energy, right? P square by 2m is it is nothing but half mv square. What is p? P is the momentum. What is momentum? M into v, mass into velocity. So, you have got m square into v square by 2m. So, m and m can be cancelled. So, this will be the half mv square, right? This is nothing but half mv square, the kinetic energy of any classical particle. So, plus v gives the total energy. Okay. So, which can be solved for the momentum we obtain. P is equal to, from this expression you can write your p square is equal to, v x will go to the left hand side, E minus V x will be P square by 2m, P square will be 2m will come here, 2m into E minus V x, right. This is what I have written here, 2m into V minus x. P means you have to take the square root. So, to the power 1 by 2. So, the momentum will be equal to 2m into E minus V x to the power of half. Now, this is a very important thing. What was done in quantum mechanics is, you do not consider the electron or any microscopic particle as a particle, but you make use of the matter wave concept. That is the crucial point. You introduce the de Broglie matter wave concept. Lambda is equal to h by p. What is de Broglie concept? You have lambda. What is lambda? I ask very often. Lambda is I make a statement. Lambda is the wavelength of the particle. P is the momentum of the wave. You have to tell me now whether the statement is right or wrong. Lambda is the wavelength of the particle and P is the momentum of the wave. Is it right or not? It should be, lambda should be wavelength of the wave and not the particle. Lambda is the wavelength of the wave and P is the momentum of the wave is wrong, momentum of the particle. So, the particle aspect and the wave aspect, wavelength of the wave and the momentum of the particle, they are beautifully connected by the de Broglie formula. The de Broglie formula connects the momentum of the particle aspect and wavelength of the wave aspect and the particle aspect are beautifully connected by the de Broglie formula, incorporating the well known Planck's constant. Is a beautiful equation, right? The matter wave concept, matter and wave, the wavelength of the wave and the momentum of the matter or the material particle. Okay, they are connected by the de Broglie formula. Now you can write lambda equal to h by p is this, right? P is the expression that you got here. So you write the equation here. The term omega square by b square will become omega square b square, that will be equal to omega, what is what? And the angular frequency will be 2 pi times nu. So obviously it will become 4 pi square nu square by b square. So nu square by b square will be equal to lambda, right? Nu square by b square will be equal to lambda. So 4 pi square by lambda square, that will become equal to 2m into e minus bx by h bar square. Okay, that is what you are getting now for omega square by b square. So when this result is substituted in the equation, we obtain the famous time independent Schrodinger equation d square psi by dx square plus 2m by h bar square into e minus bx into psi of x is equal to 0, which is almost always written in the form h bar square by 2m minus h bar square by 2m into d square psi by dx square plus v of x into psi of x is equal to e into psi of x. Okay, this is the whole thing that you have got here is called a Hamiltonian. So h operating on psi will be e operating on psi. Okay, h is called Hamiltonian. Okay, okay, otherwise you write the equation. This is a one dimensional Schrodinger equation. Okay, this single particle one dimensional equation can easily be extended to the case of 3 dimensions, because electrons are revolving in atoms and molecules. They are 3 dimensional objects. So we have to have a 3 dimensional wave equation which goes like, instead of d square psi by dx square, you have to use the Laplacian operator h minus h bar square by 2m into del square psi of r into x, r refers to x y z plus b of r into psi of r is equal to e into psi of r. This is the famous Schrodinger's time independent equation which has to be solved for electron, an atom or molecule or the rigid rotator. So many other all the problems that you come across should be solved using the equation which I showed just now. We are now ready to consider the time dependent Schrodinger equation. This is so called time independent, right? There is no time coming here, t is not found anywhere. The summary of this lecture goes as follows. The outputs of the Schrodinger equation are the eigen values and eigen functions. The eigen values are those which can be measured. The eigen functions cannot be measured, but the probability densities can be compared with the experimental values. Now we will pass on to the question session. The questions are: state the Schrodinger time independent equation. What do you understand by the terms eigen value and eigen functions? What are the outputs of the Schrodinger wave equation? Whether the above can be experimentally measured. Rest of the things such as the Schrodinger's time dependent wave equation and the outline of the problems which are going to be discussed, wherein we will be make use of the Schrodinger equation. We will see in the lectures to come. Thank you.